Okay, our first video on Cayley's theorem. So I'm sort of new at this. First video is likely to be a little clunky. I may or may not get better as we go on. A little bit of history. So Cayley's theorem first appeared in 1854, proved by Arthur Cayley, now known as Cayley's theorem. And here's what it says. For every group G star, there is a set A such that G star is isomorphic to a subgroup of the group of all permutations of A. So remember, S sub A is our shorthand for the group of all, set of all permutations of the set A. And here's a formal statement of the theorem, which doesn't differ from the previous slide. So for every group G, you can find a set A, so that G star is isomorphic to a subgroup of S sub A using the operation of composition. So we're going to take a quick look at the proof at the end of these slides, but first we're going to look at an example. And the example will be the group U sub 8 using the operation times sub 8. So remember, U sub 8 consists of the numbers 1, 3, 5, and 7. So these are the numbers between 1 and 7 that are relatively prime to 8. Okay, according to Cayley's theorem, there is a set A such that U sub 8 times sub 8 is isomorphic to a subgroup of the group of all permutations on A. So this is an existence statement. So to prove it, we have to first produce a set A. We have to say what the set A is that we will use. And the A that we will use is the set consisting of the integers 1, 3, 5, and 7. So note that A and U sub 8 are identical. This is possibly could be a little confusing, but we're thinking of this set in two different ways. When we call it U sub 8, we're thinking of it as being the elements of a group. When we call it capital A, we're thinking of it as being a set of numbers that we're going to permute. Okay, so once we've got the set A, we have to find a subgroup of S sub A and a function f from U sub 8 to this subgroup, and then we have to show that f is an isomorphism. This is a brief outline of how we have to proceed from this point. Okay, turns out it's easier to define the function f first rather than find the subgroup of S sub A. Once we get the function f defined, the subgroup will just be the range of f. Okay, so we're looking for a function f that associates with each element of U sub 8 some permutation of the set A. Okay, why don't we start with f of 3. So f of 3 is an element of U sub 8. F of 3 should be a permutation of S sub A. Well, since f of 3 is a permutation, sticking with our convention of using Greek letters for permutations, we will call f of 3 pi sub 3. Okay, so f of 3 equals pi sub 3 is a permutation of the set A, or will be a permutation of the set A as soon as we decide which one it is. So it will look like this. If you write a permutation of A in matrix form, the elements of A, 1, 3, 5, and 7 will appear in the top row, and below each element of the top row will appear the outputs. Below 1 will be pi sub 3 of 1, below 3 will be pi sub 3 of 3, and so on. So to get pi sub 3, we just have to figure out how to fill in the boxes here. How do we fill in the box below each element of A? The answer is we multiply the number of the box by 3 using the operation in our group, which in our group is times sub 8. Right, so in this box, below the 1, we'll put 3 times sub 8, 1. Below 3, 3 times sub 8, 3. Below 5, 3 times sub 8, 5. And below 7, 3 times sub 8, 7. Right, so here's a repeat of what I just said. Below 1, in this box goes 3 times sub 8, 1. That means that pi sub 3 of 1 we get by multiplying 1 by 3 using times sub 8. Below 3, we're putting 3 times sub 3, 3 times sub 8, 3. That means pi sub 3 of 3 is what you get when you multiply 3 by 3 using times sub 8, and so on. Pi sub 3 of 5 is the result of multiplying 3 by 5, and pi sub 3 of 7 we get by multiplying 3 by 7. So the result is this. Here's the matrix form of pi sub 3 before we do the multiplying, and here it is after we do the multiplying. Right, so for example, 3 times sub 8, 5 is 7. And leaving out the middle term of the equation, pi sub 3 is the permutation which in matrix form has top row 1, 3, 5, 7, bottom row 3, 1, 7, 5. Okay, we're going to do the same thing for any x in A. Same thing we did with 3 in the previous slides. We'll define f of x by f of x equals pi sub x, and pi sub x is the permutation of A defined by pi sub x of y is x times sub 8y. Right, the output of the function pi sub x, when the input is y, will be the result of multiplying y by x using times sub 8. Same kind of thing happens, almost an identical thing happens in the general case where G star can be any group. In proving Cayley's theorem, given a group G star, we will let A equal G. For each element x of G, we'll define a function pi sub x from A into A. How do you get pi sub x of y? You multiply y by x using the operation on the group G. Okay, then here's what we would have to argue to finish off the proof. First of all, we would have to argue that each of these pi sub x's is in S sub A. we would have to argue that pi sub x for each x in G is 1 to 1 and on to A. Secondly, we would have to argue that the set of these pi sub x's is a subgroup of the group of all permutations of f sub A. This is going to be the subgroup which the theorem says exist. And finally, we'd have to argue that this function f, defined by f of x equals pi sub x, is an isomorphism of the two groups.